Hello. So today I'm presenting LiDAR, which stands for Physical Laser Attacks Against LiDAR-based 3D Object Detection in Autonomous Vehicles. It was published at IEE Security and Privacy in 2023. Self-driving cars can use LiDAR to see the world in 3D. This paper shows how an attacker with a laser can inject fake data into that sensor, making the car either see obstacles that aren't there or miss ones that are. And crucially, it's the first work that actually pulls this off physically against real sensors rather than just in a simulation. So, what we'll cover today. Our agenda is we'll start with some background on how LiDAR perception works fundamentally and why it's safety critical. Then the problem, the gap in earlier work, and the threat model, meaning what the attacker actually needs. The core of the attack is itself, which has four modules. Then the four attack types, the evaluation results, and finally defenses and takeaways. So, some background. Um, let's start with how an autonomous vehicle sees the world and why that sense can be fooled. How lidar perception works. Lidar is like radar but with light. So we have a spinning array of infrared lasers firing rapid pulses in all directions. Each pulse bounces off something and returns, and by measuring the time of flight, the round trip time, the sensor computes a precise distance to that surface. If you know the time and the speed of light is constant, you can easily calculate the distance. And now, if you do that thousands and thousands of times per evolution, you get a large point cloud, a dense 3D snapshot of everything around the car. The point cloud we can feed that into a deep learning model. In this paper, those specific models are point pillars, second and Apollo. The last one, which is commonly used for commercial. The model's job is to look at the cloud and say, car here, pedestrians there, and drawing a 3D box around each one. And here's the key link. Those detections drive the car's decisions, stop, steer, and yield. So if you can make the detector wrong, you can make the car make a dangerous decision. And that's the whole attack surface. So let's move on to the actual attack surface itself. Here's the core vulnerability. A mechanical LiDAR trusts every reflection it receives, and it fires and listens in a fixed, repeating rhythm the paper calls the scanning sequence. If an attacker somehow manages to learn that rhythm, they can shine a laser back into the sensor at just the right moments and inject fake points. Points the LiDAR can't tell apart from real ones. Three things make this serious. First, it's a sensor level attack, not a software attack, not a software hack. The attacker never touches the car's code or network. It all happens in physics at the sensor, so firewalls, encryption, authentications are simply bypassed. Second, it's invisible to the people in the car. The lasers are 905 nanometer infrared. A human sees nothing. The paper even tested day, cloudy, and night conditions and found lighting barely matters because the LiDAR filters for its own wavelength anyways. Third, there are two dangerous goals. And this is where I would say it's one of the most important parts of the paper. It's hiding, which makes a real object vanish. For example, like a pedestrian. And creating, making a phantom appear. Remember those two words, hiding and creating, because the entire text taxonomy is built on them. So let's now move on to part of the paper, which is the gap in the threat model. Why prior attacks fell short and what this attacker can do. So, why earlier attacks fell short? Earlier works had four gaps. First and most important, prior laser attacks were evaluated only in simulation. Researchers like Kao, Sun, and Shen showed detectors could be fooled by adversarial point clouds digitally, but no one had actually injected such a cloud into a real LiDAR and shown it works. There's a huge gap between I edited a file and I did this with a real sensor in a real environment. Second, the physical injection that did exist could only place about 200 points at most. That's not enough, unfortunately, to build a conventionally shaped object at the chosen point. Third, there was little control over shape or distance because the injected points weren't synchronized to the LiDAR's scanning cycle. And that leads to the headline contribution. This is the first physical laser attack to actually spoof 3D object detection by injecting adversarial point clouds into a real LiDAR. That first is what makes this a standout paper. So now, in the threat model, what the attacker needs. So it needs three things. First, LiDAR parameter awareness. The attacker buys the LiDAR of the same model as the victims, reads its manual for the fixed parameters, and physically measures its rotation speed using a photodiode and an oscilloscope. So nothing you can't find commercially. Like this isn't any custom. And then second, commodity attack hardware. A photoelectric sensor to listen, an arbitrary waveform generator to time the pulses, and a laser transmitter to fire them. All off the shelf, and the paper shows it's mounted on a car. Third, and this is a nice detail, detector knowledge is only sometimes needed. So we have the optimization-based attacks, which assume white box access to the detector, but the two simpler attacks, which the paper lists as naive hiding and record-based creating, need no knowledge of the detector at all. That makes them, in practice, much more realistic threats because a real attacker usually won't know exactly which model the car runs. So that leads us to the actual details of the LiDAR attack. 4 modules that turn a desired point cloud into precise laser pulses. So let's go over the attack overflow. So module A is the parameter measurement. This is for the optimized attack. So we have the attacker measures the victim's scanning sequence, rotation speed, and horizontal resolution. There's a clever correction step here. The real timing drifts slightly from the official spec, as most devices do in practicality, so which would distort the injected cloud. So they inject a test wall, see how it works, and correct the timing. Now for the second part is the point cloud generation. They build it in 2 ways. The record-based method literally records a real object, say a pedestrian, with a substitute LiDAR, so the fake cloud already looks physically correct. The optimization-based method uses adversarial machine learning to craft a cloud that fools the detector with fewer points, but this one does need white box access. The third one is the control signal design. This is the translation layer. It converts each target's point's 3D coordinates into the exact firing timing of a laser pulse. Because in this system, when you fire, determines where the point lands. And finally, we have the synchronization. The device senses the victim's outgoing pulses, computes a precise delay, and fires so the injected points land exactly where intended. So the final flow is this. Measure the sensor, generate a cloud, encode it as pulse timings, and fire it in sync with the victim's LiDAR. So the key unlock. 2 things make this work where prior attacks couldn't. The first is raw injection power. This paper showed that they went up to 4,200 controllable points, up about 20 times the previous best of 200. They achieved this with a laser wall pattern that spans a 30 by 30 degree area, and it's precise. 90% of injected points land within about 10 centimeters of their target distance, at least within a central 20-degree window. The second is synchronization. On the right, the device senses each LiDAR pulse and fires back after a precisely computed delay. That closed loop, sense, delay, fire, is what lets the attacker place a chosen shape at a chosen distance instead of just scattering random noise. And the scanning sequence correction I mentioned snaps the spoofed wall back into shape when tiny timing offsets would otherwise distort it. Put simply, prior work could make noise, random noise, while LiDAR can drop. So let's go over more in detail about the 4 attack types. Keeping in mind that the 2 goals are hiding and creating, each done in kind of a naive black box method, and each one done also in optimized way, considering white box access and some nice math. So here's the matrix. We have 2 goals, hiding and creating, and 2 methods. Naive hiding. Okay, so we have that on the top left, and that's inject a fake wall of points far away. The detector fixates on that wall and drops the real object nearby. Simple and needs no knowledge of the detector. Record-based grading. You replay a point cloud you pre-recorded from a real object or real pedestrian to conjure a convincing phantom. Also needs no detector knowledge. Then we have optimization-based hiding. Here you use adversarial ML, machine learning, to craft points placed just above the target that suppress its detection box. This needs white box access, but achieves the effect. Here's the key point, with fewer points. So fewer energy, and it's more optimized. Same thing with optimization-based grading. Same idea, opposite goal, optimize points in a target region to force a false detection. The elegant thing is the trade-off. Record-based methods are knowledge-free but need more points. Optimization methods need white box access but are more efficient. An attacker picks based on what they know and what hardware they have. Now we get to the evaluation stage. So how well does it actually work? They tested three ways: in simulation, on real hardware, and a moving vehicle between two moving cars. The setup is thorough. Two real LiDARs, the Velodyne VLP-16 and RoboSense RS-16, the two most common mechanical LiDARs, plus the HDL 64E in simulation. Three detectors, point pillars, and second from academia, and Apollo, a production commercial system. They used the standard KITTI dataset targeting the three classes that matter: car, pedestrian, cyclist. And the metric throughout is attack success rate, successful attacks over total attempts. They collected 2,400 frames in the physical tests alone, so this is a substantial evaluation. So let's go over the actual physical attack success rates. Here are the real physical results, and the pattern is striking. Naive hiding hits 100% on every single detector in LiDAR. That is by far the scariest result because it's the easiest attack. No detector knowledge, and it always worked. Hiding a real object reliably with the simplest method. Record-based grading stays high too, around 81% representative, up to 98% on some detectors. The optimization-based attacks are harder in the physical world, roughly 61% for hiding and only 36% for grading in these representative numbers. Because they demand tighter control over every point and real-world laser intensity and jitter fight against that, but they still succeed a large fraction of the time. The color coding. Red bars are hiding, green are creating. The takeaways is that the simplest knowledge-free attacks are actually the most reliable, which is exactly backwards from what you would hope as a defender, because they're simpler for the attacker. And now, what moves the numbers? Four factors shift success rates. LiDAR model, the VLP-16 averaged about 71% success versus 60% on the RS-16. The RS-16 has a pulse randomizing feature, periodic silent gaps that makes precise injection harder. That's a hint at defense, and we'll come back to it. Now, the distance. Hiding stays near 100% as you move further away, but creating and optimization attacks fall off because the laser intensity drops and fine control degrades. And now the angle. Attacks work best within roughly 15 degrees horizontally, limited by the LiDAR's receiver's field of view. And finally, the install height. Optimization attacks peak around 1.7 meters, which happens to be the height of the LiDAR that collected the KITTI training set. So the attacker's effectiveness partially reflects the training data, which is an interesting detail. Now, from lab to road. Moving vehicle. This is the strongest evidence in the paper. They put both the attacker and the victim in moving cars, driving at only about 5 kilometers an hour, 5 to 15 meters apart, and ran the attack live. Hiding succeeded 94.1% of the time, 16 out of 17 trials. Creating succeeded 78.9%, 15 out of 19. To handle the jitter from the motion, they widened the receiver with a telescope and used a bigger laser spot. There's one honest limitation, though, here. At the bottom, when only the victim moves and the attacker is stationary, aiming the invisible infrared laser in real time is still an unsolved engineering problem. So it's not effortless, but a moving to moving attack clearly works, and that's a genuinely alarming result. So let's talk about some defenses and takeaways that the paper suggested. How to raise the bar from a defense point of view. The paper suggests three complementary defenses. Each raises the attacker's costs rather than fully closing the door. Rotation speed customization. The attacker's timing is tuned to the victim's exact RPM, rotations per minute. So if the card changes its LiDAR's RPM from time to time, the injected cloud deforms. The attacker can remeasure it, but it costs them time and effort. Pulse coding and randomization. Encode or randomize the LiDAR's own pulses and reject any of the foreign ones, similar to anti-jamming techniques in military radar. We already saw a hint this works since the RS-16's randomization lowered success rates. The trade-off is cost and sensor robustness. And the third is multi-sensor fusion and redundancy. Cross-check LiDAR against cameras, radar, and ultrasonic sensors. If the LiDAR says obstacle but the camera sees clear road, the disagreement flags a spoof. And now, key takeaways. 5 things to remember. 1. Cloud LiDAR is the first attack to physically spoof 3D object detection by laser injecting adversarial point clouds into a real LiDAR. 2. A stronger transceiver injects roughly 4,200 controllable points, about 20 times prior work, enough to forge convincing objects. 3. 4 attack types across 2 goals. Hiding and creating, some needing no knowledge of the detector at all. 4. It works on 2 commercial LiDARs, 3 detectors, and even between 2 moving cars, with 94% hiding and 79% creating. 5. Defenses exist, but none is complete. Sensor security is now a first-class concern for autonomous vehicles, not an afterthought. And realistically, in our time, there are more and more autonomous vehicles getting on the road, and more companies are investing in autonomous vehicles. So these findings can become more relevant, and it's important to work on the defense side of it to make sure that there are appropriate defenses for such attacks, especially the naive ones, where they're not optimized and randomization won't necessarily do anything. So the deeper lesson as we hand life and death decisions to machine perception, the sensors themselves become an attack surface, and we have to defend them like one. Thank you. That's Ply LiDAR in one line, a laser into the self-driving car's LiDAR can make it see ghosts or go blind, and the authors proved it in this physical world, even on the move. Thank you, and I'll be happy to answer any questions in a discussion.